First discovered in 2017, Object 1I/2017 U1, also known as Oumuamua, has captivated the imagination of astronomers and space enthusiasts ever since. Initially identified as a comet, Oumuamua quickly revealed itself to be unlike any object previously observed within our solar system. This interstellar object, the first of its kind, defied conventional classification, sparking intense scientific interest and speculation about its origin and composition. As researchers continue to analyze and debate the nature of Oumuamua, its discovery has also opened the door to further exploration of interstellar objects. Brace yourself because Oumuamua is acting weird and moving towards Earth. Today, we'll explore all there is to know about this peculiar object, its oddities, and why it matters to us. Object 1I/2017 U1 or Oumuamua made history as the first interstellar object ever detected traversing through our solar system. Using the Pan-STARRS telescope at Haleakala Observatory, Hawaii, Canadian astronomer Robert Warwick spotted this intriguing celestial visitor on October 19, 2017, roughly 40 days following its closest approach to the Sun on September 9. At the time of its discovery, Oumuamua was situated about 33 million kilometers or 21 million miles from Earth. This distance is approximately 85 times farther than the Moon. When it was first detected, the object was already journeying away from the Sun, measuring between 101,000 meters, or 303,000 feet, in length. Oumuamua is a relatively small object, with an estimated width and thickness ranging from 35 to 167 meters, or 115 to 548 feet. Sporting a reddish hue, much like the objects found in the outer regions of our solar system, Oumuamua piqued scientific curiosity because it lacks a coma, which is a nebulous envelope of gas and dust that are released from the comet's nucleus as it approaches the Sun and heats up. The coma is typically illuminated by the Sun and can extend for thousands or even millions of kilometers in size. Since the object was initially thought of as a comet and lacked a coma, which is a typical feature surrounding comets formed when they approach the Sun, scientists began exploring other possibilities. It also displayed non-gravitational acceleration, potentially attributed to outgassing or solar radiation pressure. Moreover, its elongated shape surpassed that of most natural celestial bodies observed, sparking debates about its origins. Oumuamua's peculiar motion, appearing more like tumbling than spinning, coupled with its rapid pace relative to the Sun, suggested that it came from outside our solar system. Its trajectory indicated it would depart the solar system and venture further into interstellar space, its planetary system of origin and age shrouded in mystery. Its appellation, Oumuamua, stems from the Hawaiian language and means scout or messenger. This designation underscores its role as a herald from the distant past, symbolically reaching out to humanity. Translating roughly to first distant messenger, the name embodies its significance. The Pan-STARRS team collaborated with Kaiu Kimura and Larry Kimura from the University of Hawaii at Hilo in selecting this name, honoring its cultural and linguistic roots. Initially designated as Comet C/2017 U1 due to its strongly hyperbolic trajectory, Oumuamua was reassessed later as observations unfolded. Subsequent deep-stacked images revealed that it lacked a coma, prompting a reclassification as Asteroid A/2017 U1. This was the first instance of a comet being redesignated as an asteroid. Comets are composed of ice, dust, and rocky material, while asteroids are primarily made of rock and metal. When observed through telescopes, comets often appear with a fuzzy, glowing coma and a tail, which is formed when the coma is blown away by the solar wind. This tail gives comets a distinctive appearance in the night sky. Reclassifying a comet as an asteroid was thus a big deal. However, even this did not solve the enigma surrounding this odd celestial object. Upon confirmation of its interstellar origin, Oumuamua received the designation 1I/2017 U1, inaugurating a new class of objects. The name 1I/2017 U1, which is the first of its kind, carries significant scientific weight. The 1I prefix denotes its status as the first ever identified interstellar object. The 2017 component reflects the year it was first observed. Furthermore, the U1 designation signifies its discovery during the initial half of October. Another mystery surrounding the object was a non-gravitational boost to its acceleration. A non-gravitational boost is an unexpected increase in velocity that cannot be solely attributed to gravitational forces. In other words, there was an additional acceleration observed beyond what would be expected from the gravitational influence of the Sun and other celestial bodies. In the context of Oumuamua, it suggests the presence of a source of propulsion or force acting on the object. The observed non-gravitational acceleration of Oumuamua raised intriguing questions about its nature and composition. It led to speculation that the object might exhibit comet-like behavior, such as outgassing, where volatile substances vaporize and create thrust as they are released from the surface due to solar heating. However, despite extensive observations, no such outgassing or coma was detected, leaving the exact cause of the non-gravitational acceleration unresolved. This fueled speculation about its possible artificial origin or exotic composition. Moreover, spectral analyses revealed a red color like comet nuclei or trojans, along with featureless, red-colored spectra resembling Kuiper belt objects. Light curve observations indicated a tumbling motion rather than rotation around its principal axis, potentially triggered by a collision following its origin. The object's shape, inferred from light curve variations, ranges from highly elongated cigar-like to extremely flat. Despite its physical unremarkableness, Oumuamua's highly elongated shape remains a subject of intrigue. Spectroscopic analyses indicate that the interstellar object has a dense metal-rich rock composition. It may also have internal ice, shielded by an insulating mantle from cosmic ray exposure. Notably, debates continue regarding its compositional nature, with hypotheses ranging from dense conglomerates of dust and ice grains to frozen hydrogen. However, in December 2017, Avi Loeb, an astronomer from Harvard University and advisor to the Breakthrough Listen project, proposed investigating Oumuamua's potential artificial origin by examining radio emissions. He said so because of the object's unusually elongated shape. The Green Bank Telescope in West Virginia was enlisted for this purpose, aiming to detect any unexpected radio signals indicative of artificiality. Despite earlier efforts by radio telescopes such as the SETI Institute's Allen Telescope Array yielding no results, the Green Bank Telescope conducted a 6-hour observation of Oumuamua across 4 bands of radio frequency on December 13, 2017. However, no discernible radio signals were detected within this limited scanning range, prompting the need for further observations. Of course, this was not enough to dismiss the possible artificial origin of this interstellar object. Key observations and conclusions regarding Oumuamua's trajectory and characteristics were primarily derived from data collected by various telescopes, including the Pan-STARRS 1 telescope and the Canada, France, Hawaii telescope. Detailed analyses of its composition and shape were conducted using advanced telescopes like the Very Large Telescope, the Gemini South Telescope, and the Keck 2 telescope. This, supplemented by input from notable astronomers, contributed to the extensive observations and research, culminating in a publication in Nature on November 20, 2017. Despite its initial visibility, Oumuamua progressively faded from view by 2020, rendering it challenging to study further. However, what we know for sure is that its path is characterized by retrograde loops and an eccentricity of 1.20, the highest ever observed. Retrograde loops suggest that when observed from Earth, the object's apparent motion seems to form loops in the sky, which is unusual as most celestial objects follow a more straightforward trajectory. Eccentricity, on the other hand, measures how much an orbit deviates from a perfect circle. An eccentricity of 1.20 is exceptionally high, indicating an elongated and hyperbolic orbit. This extreme eccentricity implies that Oumuamua's path is highly elongated and not bound by the Sun's gravitational pull, further highlighting its interstellar origin and unusual characteristics. As if this was not odd enough, Oumuamua's journey through the solar system showcased a significant gravitational interaction with the Sun, resulting in a sharp turn northward at its closest approach on September 9, 2017. As Oumuamua continues its journey away from the Sun, it will gradually slow down, maintaining a relative speed of 26.33 kilometers per second. Astronomers estimate that 100 years ago, Oumuamua was approximately 83.9 billion kilometers, or 52.1 billion miles, from the Sun, traveling at 26.33 kilometers per second relative to it. This velocity aligns closely with the local standard of rest in the Milky Way, again indicating an extrasolar origin. Oumuamua may have been ejected from a stellar system, such as Carina or Columba, potentially several billion years ago. Alternative theories propose that it may have originated from a white dwarf system or as a fragment from a tidally disrupted planet. Another hypothesis suggests it could be a member of a class of small hydrogen ice-rich bodies formed in the cores of giant molecular clouds. But so far, conclusive evidence eludes us. This is not to say that scientists have not explored rational explanations for the oddities associated with Oumuamua. One such explanation is the nitrogen ice theory. This hypothesis suggests the presence of nitrogen ice to explain the absence of outgassing from Oumuamua. Scientists propose that this ice could have survived for up to 500 million years in the interstellar medium. Nitrogen ice of Oumuamua's size would reflect approximately 2/3 of the Sun's light. This theory gained further support in March 2021 when scientists presented a related theory, positing that Oumuamua might be a fragment of an exoplanet resembling Pluto, referred to as an exopluto, originating from beyond our solar system. However, this theory has faced criticism from Professor Avi Loeb. In November 2021, theoretical studies by Siraj and Loeb suggested that Oumuamua was not a nitrogen iceberg. Another proposed theory suggests that Oumuamua could contain a significant amount of hydrogen ice. This hypothesis implies that the object originated from the core of an interstellar molecular cloud, where conditions conducive to the formation of such material may exist. Sublimation of hydrogen due to the Sun's heat propelled the body, creating a coma that might be challenging to detect from Earth-based telescopes due to atmospheric limitations. This theory could potentially explain Oumuamua's significant non-gravitational acceleration without exhibiting signs of coma formation. However, subsequent studies have shown that hydrogen icebergs cannot form from small grains and would likely have evaporated during their journey in interstellar space under the given circumstances. In 2023, an alternative theory proposed that the observed non-gravitational acceleration and spectrum of Oumuamua could be best explained by hydrogen outgassing from a water ice matrix. This theory suggests that hydrogen buildup in the water ice occurred during the object's journey through interstellar space. However, Avi Loeb, a distinguished astrophysicist, alongside Frank B. Baird Jr., a professor of science at Harvard University, defies conventional approaches to the matter. He believes that Oumuamua could be proof of alien life nearby. This means a lot coming from a man of his stature. From his early days studying the birth of stars at Princeton to his groundbreaking contributions at Harvard's Institute for Theory and Computation, Loeb's journey has been marked by a relentless pursuit of understanding the cosmos. While many proposed conventional explanations, Loeb ventured into uncharted territory, suggesting that Oumuamua could be of extraterrestrial origin, a notion that raised eyebrows among his peers. His bold proposition, articulated in his book Extraterrestrial, The First Sign of Intelligent Life Beyond Earth, sparked both fascination and controversy. Undeterred by skepticism, Loeb embarked on the Galileo project, aiming to monitor the skies for evidence of extraterrestrial technology, a venture reflecting his willingness to challenge scientific orthodoxy. Despite criticisms and debates surrounding his ideas, Loeb remains undaunted, driven by a fervent curiosity to unravel the mysteries of the universe. He is also reshaping the search for extraterrestrial intelligence, or SETI, with his pioneering methods. Departing from traditional radio signal detection, Loeb advocates for the exploration of physical artifacts and chemical byproducts of alien technology, a bold stance that challenges established norms in the scientific community. Despite skepticism, Loeb sees potential synergies between his approach and conventional SETI methods, envisioning a collaborative effort to uncover hard evidence. His optimism is fueled by advancements in astronomical technology, notably the Vera C. Rubin Observatory in Chile. This state-of-the-art facility can capture unprecedentedly detailed images of billions of galaxies, revolutionizing the field of space archaeology, a term coined by Loeb to describe his quest for extraterrestrial artifacts. From the origins of the universe to the nature of human consciousness, he has embraced uncertainty and pushed the limits of empirical knowledge. Loeb embodies the spirit of scientific exploration, challenging entrenched paradigms and advocating for a broader, more inclusive approach to understanding the cosmos. He remains steadfast in his conviction that curiosity, innovation, and rigorous empirical inquiry are essential drivers of progress. Whether probing the mysteries of dark matter or contemplating the existence of extraterrestrial civilizations, Loeb's insatiable curiosity and unwavering determination continue to inspire both colleagues and aspiring scientists alike, reminding us that the quest for knowledge knows no bounds. Coming back to our peculiar visitor, in a groundbreaking study titled "Could Solar Radiation Pressure Explain Oumuamua's Peculiar Acceleration?" Shmuel Bialy and Avi Loeb proposed a compelling alternative explanation for the mysterious behavior of the interstellar object. Bialy and Loeb raise critical questions regarding its lack of expected outgassing when closest to the Sun, as well as the absence of significant spin evolution, which is typically associated with cometary activity. The duo suggested that Oumuamua may, in fact, be a light sail or a form of spacecraft propelled by radiation pressure. This intriguing possibility prompts a re-evaluation of Oumuamua's origins and purpose, raising the tantalizing prospect of extraterrestrial exploration within our solar system. As Professor Loeb elaborates, the observed acceleration of Oumuamua away from the Sun could be attributed to sunlight exerting force on its surface. This would require an extraordinarily thin structure, mere fractions of a millimeter in thickness, but tens of meters in size. Such dimensions would enable Oumuamua to function as a light sail, facilitating propulsion through the vast expanse of interstellar space. For perspective, imagine Oumuamua as a sailboat navigating the vast ocean of interstellar space. However, unlike traditional sailboats powered by wind, Oumuamua harnesses the force of sunlight to propel itself forward. In this analogy, the sail of the sailboat corresponds to Oumuamua's ultra-thin structure, which is described as being only fractions of a millimeter thick. Despite its thinness, this sail stretches across tens of meters, providing a large surface area to capture the pressure exerted by sunlight. This radiation pressure arises from the transfer of momentum when photons, or particles of light, collide with an object. Although photons have no mass, they carry momentum due to their energy and motion. Thus, when sunlight strikes an object, photons are absorbed or reflected by the object's surface. As photons are absorbed, their momentum is transferred to the object, resulting in a tiny but continuous push away from the light source. The more photons that are absorbed or reflected by the object's surface, the greater the force exerted by radiation pressure. In the case of Oumuamua, if it is indeed a large, ultra-thin sail-like structure, it will be able to provide a significant surface area for harnessing radiation pressure and generating propulsion through space. Much like how the wind fills the sails of a sailboat, sunlight exerts pressure on Oumuamua's sail-like structure. By effectively sailing on the radiation pressure generated by sunlight, Oumuamua can traverse the vast expanse of interstellar space with remarkable efficiency. However, just as a sailboat's sail must be positioned and oriented to catch the wind effectively, Oumuamua's thin structure must be precisely angled to intercept sunlight and harness its propulsion force. Loeb's provocative conjecture posits Oumuamua as either a naturally occurring artifact or an artificial probe deployed for reconnaissance purposes. Undertaking meticulous calculations, Bialy and Loeb explored the feasibility of an artificial light sail surviving the rigors of interstellar travel. Their findings suggest that a sail of minimal thickness, ranging from 0.3 to 0.9 millimeters, could indeed withstand interstellar conditions. Furthermore, the duo speculate on potential scenarios involving Oumuamua's presence in our solar system, proposing that it may function as a derelict sail adrift under gravitational and stellar influences, pretty much like maritime wrecks adrift in terrestrial oceans. This hypothesis offers a compelling rationale for the absence of detectable radio transmissions. Professor Loeb contemplates Oumuamua as a harbinger of space archaeology, a pioneering field poised to investigate relics of extraterrestrial civilizations. Drawing parallels to human-designed light sails, such as the Japanese Icaros project and the Starshot initiative, Loeb envisions Oumuamua as a testament to humanity's quest for cosmic exploration. Moreover, Professor Loeb raises the possibility of Oumuamua being deployed by an advanced extraterrestrial civilization to investigate our solar system. This idea parallels humanity's aspirations for interstellar exploration. This hypothesis challenges conventional notions of Oumuamua's random trajectory, suggesting deliberate intent behind its journey. After all, did the object not come in close proximity to Earth and display strategic orbital maneuvers? Amidst the uncertainties, Bialy and Loeb have explored the transformative potential of interdisciplinary inquiry and the inexhaustible mysteries awaiting exploration within the cosmos. Whether Oumuamua represents a natural anomaly or an artifact of alien technology, its enigmatic presence invites humanity to embark on a journey of discovery spanning the depths of interstellar space. Another chapter in this saga opened up when an image capturing Oumuamua came to light. This deep combined image, created by merging data from the European Southern Observatory's Very Large Telescope and the Gemini South Telescope, provides a comprehensive view of Oumuamua's surroundings and allows astronomers to study its peculiarities in detail. The interstellar object is visible at the center, distinguishable by its unique features amidst a backdrop of stars. Unlike typical celestial objects, Oumuamua stands out due to its distinct appearance. Visually, Oumuamua appears as a point source in the image, marked by a blue circle. This implies that it emits or reflects light concentrated at a single point, rather than being surrounded by dust or other material commonly seen around celestial bodies like comets or asteroids. The trails of faint stars surrounding Oumuamua appear smeared in the image. This is because the telescopes were tracking the moving object. This motion blur highlights the dynamic nature of Oumuamua's journey through space, contrasting with the stationary appearance of stars. Traveling at speeds of tens of kilometers per second, Oumuamua's rapid motion makes it challenging for telescopes to capture clear, detailed images. Overall, the visual depiction of Oumuamua differs from traditional celestial objects due to its unique appearance and the absence of surrounding dust or debris, setting it apart as an intriguing and unusual interstellar visitor. If we were to take Loeb's hypothesis seriously, the possibility of Oumuamua being an extraterrestrial craft opens up a realm of speculation and excitement in our understanding of interstellar technology. While we have developed sophisticated missions like Voyager to explore our immediate surroundings, encountering an object like Oumuamua presents a potential first contact with an alien civilization. Unlike our spacecraft, which are meticulously engineered and programmed by human hands, Oumuamua represents a technology beyond our current capabilities. Its origin, whether natural or artificial, challenges our understanding of what is possible in the vast expanse of space. While missions like Voyager have provided invaluable insights into our solar system and beyond, they are products of human ingenuity and technological advancement. The Voyager missions, consisting of Voyager 1 and Voyager 2, are two of the most iconic and successful space exploration endeavors in human history. Launched by NASA in 1977, these spacecraft were designed to explore the outer planets of our solar system and their moons, as well as to venture into interstellar space. Equipped with an array of scientific instruments, including cameras, spectrometers, and particle detectors, the Voyager probes have provided unprecedented insights into the outer reaches of our celestial neighborhood. Both spacecraft conducted flybys of Jupiter and Saturn, with Voyager 2 additionally visiting Uranus and Neptune. During these close encounters, the probes captured detailed images and data about the planets, their atmospheres, rings, and moons. The missions also made numerous groundbreaking discoveries, including active volcanoes on Jupiter's moon Io, intricate ring systems around Saturn, and complex weather patterns on gas giants like Jupiter and Neptune. Voyager 2's flyby of Uranus and Neptune provided the first close-up views of these distant ice giants, revealing their unique characteristics and moons. After completing their primary mission objectives, both Voyager probes continued their journey outward from the Sun. In 2012, Voyager 1 became the first human-made object to enter interstellar space, followed by Voyager 2 in 2018. These milestones marked humanity's first foray into the space between the stars, offering valuable data about the conditions and boundaries of our solar system. Each Voyager probe carries a golden record, a phonograph record containing sounds and images selected to portray the diversity of life and culture on Earth. Intended as a message to any extraterrestrial civilizations that may encounter the spacecraft, the golden record is a time capsule of humanity's achievements and aspirations. Surprisingly, despite being launched over 4 decades ago, both Voyager probes continue to operate and transmit data back to Earth. Their longevity has far exceeded expectations. Both missions have expanded our understanding of the outer planets, provided valuable insights into the formation and evolution of planetary systems, and pushed the boundaries of human exploration into the depths of space. Furthermore, these probes carry messages of peace and goodwill to potential extraterrestrial civilizations. The golden records aboard the spacecraft encapsulate the diversity of life on our planet and represent humanity's desire for connection and understanding across the vastness of the cosmos. Could Oumuamua be a similar effort on the part of an entirely different civilization looking to explore life here on Earth? If it is, this may be our best chance to explore the extent of the technological prowess of these extraterrestrial beings. If Oumuamua is indeed an extraterrestrial craft as Loeb proposes, this would make it the first tangible evidence of another civilization beyond our own. This prospect ignites the imagination and raises profound questions about our place in the universe and the possibility of communication or interaction with other intelligent beings. Of course, at this point, it is impossible to say anything with absolute certainty, but even the slightest possibility is worth exploring at least. As we continue to study Oumuamua and await further discoveries, we must be mindful of the boundless mysteries that await us in the cosmos and the potential for extraordinary encounters. Well, that's it for now. Thanks for watching. Don't miss this video you see on your screen right now. It's truly unbelievable.